There we go. All right, we're now recording from the current slide, but the current slide is in Chapter 3, and we're still in Chapter 2. That's because the last slide in 2.5 wasn't on, the last example wasn't on the slide set. So let's go from here. Let's find some white space here. That may have to do. That would be better. I think we've got, oops, that wasn't bad. Let's see. That's probably going to be my best white space. All right, we're going to be backtracking in a bit. If I can get the pen to come up. Okay, come on. There we come. Okay. Maybe now we'll get started. First, any questions? Anything we've done so far? As far as I know, until July, no, I'm sorry, there's coming up one more doctor's appointment toward the end of this month, but that's on a Tuesday morning, so that won't bother this class, except that I won't be available for office hours then. But that's coming up. I'll let you know when that gets closer. Next appointment with the eye is next month, which will be around the 23rd or so of July. So that would be, again, on a Tuesday or Thursday, so it won't bother this. So any questions? Anything so far? Okay. Where we left off last time, we had done example 5 in 2.5. Chapter 2, differentiation, 2.5, implicit differentiation, and we're ready for example 6, which I think is, no, 2 more to go after this. So let's do example 6. Now, it says find dy dx implicitly for this equation. The sine of y is equal to x, and we want to find dy dx. You tell me how to begin to do that. And then later we'll talk about the interval. How would you approach it? What would you do? Did Jesus answer here? Take a derivative. Okay, how do you take a derivative of this? What's the derivative of sine? Okay, that's cosine y, though. Cosine y, and because y is a function of x, what is the next step you have to do? Take the derivative of y, which we express as, let's go and write it since they did, as dy dx. Okay, that's the left-hand side. What's the right-hand side? Derivative with respect to x. Pretty easy. 1. Good. Now what do we do? Okay, divide by cosine y. Now that should set a few warning bells off in your head. And what would those warning bells be saying? That is a correct step to do. Yes, you cannot have zeros in the denominator, and cosine of y is 0 when y is any of your half pi's. So y cannot be any half pi. Okay, and you're in here, Jalen. There you are. All right. So we're limited. Y's can't be any of your half pi's. Okay, so we'll come back to that in a little bit. Okay? Can you simplify that maybe a little bit? Not liking things in denominators as I do. What's 1 over cosine? Secant. That's the same as secant y. And, again, y can't, for secant is undefined at your half pi's because cosine is 0 there. That's one of the cosine. Okay, there's your dy dx. Okay? Now, what the... and they didn't go do that last step. Now, the second part says, find the largest interval of the form minus a is less than y. That's an ugly a, isn't it? Is less than y is less than a. Okay? On which y is a differentiable function of x. We basically just said that. You can choose any of them, but the most convenient one would be what? Negative pi halves less than y less than pi halves. Okay? It's defined everywhere in there, nowhere else. Now, you could do any other interval like that that you wanted to, half pi interval. Notice you cannot have an equal sign in either place because it cannot equal pi halves. But anything in between will be perfectly fine. And all the intervals are the same size. They're exactly pi in width, you might say, or in magnitude. Just short of pi because they don't include either input. All right. Now, then they say, I don't know why they go so far as to do this, they said find it implicitly, we did. Okay? Now, since you restrict yourself to this interval, they say you can go another step here and say that if you're restricted to that interval, then you can say, I'm not sure why. They didn't say do this, but they're showing you you can do it. A trig identity, cosine y is equal to the square root of, anyone think of what might go in there? 1 minus sine squared from your good old Pythagorean identity. Okay, and that's of y. Okay? Now, if you're limiting your y to these values, then that's a perfectly legitimate thing to do. However, it should have been a plus or a minus, but since you're limiting to these values, I think you probably still could have done plus or minus, but let's just do with the plus. And then with that in mind, you can rewrite your dy dx, though they didn't say do this, but they're doing it, as 1 over, oh, and by the way, what was sine y? X. So this is the same as the square root of 1 minus x squared. Okay? Going back to your independent variable here, so this will be the square root of 1 minus x squared. Okay? It would work okay for the minus as well, but we're going to stick with the plus. Okay? Now, they didn't say do that, but they went on and did it anyway. All right. Now, let's move on to example 7. Any questions on that one before I erase? Okay. The first part was relatively easy, but then they got into that second part that they didn't even ask for. And it wasn't hard, but it's just sort of, who cares? Okay. Maybe someone does. I'm sure someone must. Okay. So, let's do example 7. How about second derivatives? How about trying to do it implicitly? By the way, there's a little blurb on the left margin here on page 148 on Isaac Barrow. And frankly, I had never heard of Isaac Barrow before, except in relation to his student, or one of his students. I'm sure he had many. One of his students was Isaac Newton. Okay. Isaac Barrow, I think they both were, yeah. When Isaac Newton, Isaac Barrow had been and was the head honcho mathematician at whichever university, Oxford, I think it was. They don't list here in this little thing which it was. Oxford, I believe. It was either Oxford or Cambridge. Maybe it was Cambridge. But anyway, he was the head honcho there, the Lucasian chair of mathematics. So he was in charge of it all. In came this little young whippersnapper, Isaac Newton, and in 3 years, he had blown them all out of the water. I mean, he ate up everything they taught him and went beyond. And so when he finished, Isaac Barrow, really must have been a pretty amazing guy, said, hey, you take this chair, you become chair, basically acknowledging he went way beyond what Barrow had ever done. So they did work together, and it sounds like worked together well in the early development of calculus. But anyway, nice little blurb there. Except for Isaac Newton, I'm not sure many people will remember Isaac Barrow, but he was his mentor. Okay, let's go x squared, this is example 7, plus y squared is equal to 25. And I think we all know what that is, don't we? Oops, I say 25 and write 20. Something wrong with the brain here. I'm really distracted because I keep looking down here to make sure my power's still on. It's just been flicking in and out this morning, so I don't want to go through that again. All right. Anyone know what that represents? We've had it a few times before. Circle of? Tell me something a little bit more about the circle. Radius 5, perfect. Okay. Circle of radius 5. Okay. So obviously, not a function. Okay. As written. You'd have to limit. Now, let's first take a derivative of dy dx. That's what we're looking for. How would you do that? Anybody? Help me. Anyone? It's not that hard. Yes. Get me started. Derivative of x squared. Second? 2x, excellent. Okay. Plus, keep me going. 2y. Is that all? For some reason, my pen is skipping. I don't know why. Okay. I'll probably write over itself in a minute. Okay. Is that all? Dy dx. Okay. Because you're taking with respect to x, and y is a function of x. X is not a function of x. X is x. Okay. And then continue. 0. Okay. All right, let's fiddle with that a while. What we're looking for is the first derivative, right? Okay? So this is what we're seeking. What do we do now? Trying to isolate that dy dx. Get it all by itself, everything else on the other side. So where would you start? Subtract 2x from both sides? Okay, sounds like a great idea. Okay, This goes away now, and you have 2y dy dx, which is what we're looking for, is equal to minus 2x. Okay? Again, we're trying to isolate the dy dx. So what do we do next? Divide by 2y. Okay? Everything goes out here. Here the 2's go out, and you have dy dx is equal to minus x over y. Now, since the goal here is to find the second derivative of y with respect to x squared, I'm going to have to take a derivative of that. And there's two ways to approach that. What two ways can you think of? Or you may only think of one. How would you take a derivative of that? Anybody? Okay, I was afraid someone would say that. The quotient rule. And you certainly can, and that's what the book uses. I really don't like the quotient rule that much. I mean, it's fine. Good rule. It has a funny little thing, low D, high, all that kind of stuff. But I like product rule better. Can I rewrite that so I can use a product rule? Anybody? How? You have a variable in the denominator. How can you deal with that? Okay. Didn't follow all that, but did you say minus x times y to the minus 1? Say yes. Okay. Oh, that's what he said. All right, good. Okay. That now makes it a product rule problem. Product rule problem. I like those a little bit better. But you can do it either way. Okay? So what would dy dx? d2y. I've got it these. All right. d2y dx squared, which is basically the derivative of this, but let's do the product rule. And how does that go? Anybody? How does the product rule go? Uh-oh. Flip, flip, flip. Second? Second? A little louder. Okay, that's the quotient rule. If you want to use the quotient rule, we can do that. You want to do quotient rule? Ah, yeah, I knew you wanted to. Okay, we'll go that. Forget about the product rule for now. So we start with low, okay, and that's going to be, let's put the minus sign out in front, okay, and low is going to be y. What's d high? Help me somebody. 1, okay, so that's fine. Then what's next? Minus x, did you say? Is that all? That's your minus high, but I still haven't heard your... Ah, there's your dy dx, because d low is a function of x, so that's going to be dy dx, okay? So that's the numerator, and all that's over... Yes, y squared, low, low, okay. All right. Now, admittedly, it's a little messy. That's an understatement, okay? But here's what we've got to do now. We got the minus here. Y is fine, just like it is. Minus x, but now we need to put in for what dy dx is. And since y'all are doing quotient rules, let's go on and put it in. Dy dx is another minus x over y, right? That's your dy dx from right up here, okay? And that's all over y squared. All right. We got some messing to do, don't we? First thing, I want to just mess with the signs, okay? No, let's not. Let's leave that minus sign out in front, okay? Now, in the numerator, well, I'm trying to skip steps because I don't have much room, but let's write it out. Y minus, only that's going to now become a plus because it's minus times minus, x squared over y, right? Over y squared. Everybody okay with that first step? Okay. Now, we need that numerator over a common denominator, which is going to be y. So if we put this over y, we have to multiply that by y as well. So now that becomes a minus x squared plus y squared. I just rearranged the order over y squared. Well, those y's are in denominators, so we could make that to be minus x squared plus y squared over y cubed. Okay? But we know what x squared plus y squared is, don't we? Don't we? 25. So you could go back and write this as minus 25 over y cubed. Oh man, could it possibly come out that reasonably? Yes, it does. Kind of amazing, but true. Your first derivative was a function of both x and y, but the second derivative wound up just being a function of y alone. Rather bizarre, but true. Any questions? The key there is that then always don't lose the forest for the trees, you know, sort of keep the big picture and say, wait a minute, yeah, I can plug in what dy dx is up there from that one, and then when I saw this, I said, wait, that was what your original function was, 25. So, all right. Now what we didn't do was mess with what values you have to use or not use. X would only be defined from minus 5 to plus 5. And the problem being, you can't use minus 5 or plus 5 because at that place y is equal to 0. Because the only way x could be minus 5 if y is equal to 0, or plus 5. So you have to exclude that. So this is only good for, I'm sorry, I started right, minus 5 and wrote as 0. That's strange. But now the eraser's not picking up. Okay. Okay. Let's go back and get that again. Minus 5 is less than x is less than 5. Okay. And, well, 5 does, there it goes. And the bizarre thing here is, it doesn't really matter on the second derivative because x doesn't show up anywhere down there. But we still haven't determined whether we're going to deal with the plus or the minus. You know, because this is a circle, we're going to deal with top half or bottom half. But I hope you remember your second derivative refers to what? Ooh. Oh, no, we haven't gotten there yet, have we? Sorry, I was thinking my other class. Yeah, we haven't done concavity yet, right? Okay, sorry. It still doesn't tell you anything. What it refers to is whether it's concave down or concave up. If it's positive, it would be concave up. If it's down, negative, it's concave down. But you still don't know, because if y is positive, then this thing is negative, so it's concave down. But if y is negative, this thing is positive. So you have to choose, but this doesn't give you any hint which way you need to go with it. So you just choose whether you're going to use positive x, positive y's, or negative y's. But that's beyond what the problem was asking. So, but it's not a bad idea to think through those. Let's go on to example 8, which we'll have to do on this same restricted space as well. Any questions before I erase it? Okay. Example 8. Find the tangent line to the graph of x squared times x squared plus y squared. Oh, the 10 o'clock scholar. Okay, rhymes here. All right, good deal. Still, except for poor old Demiri, you're the only one holding down the bottom half of the alphabet. Top half is perfect attendance. You're the only one here from the bottom half of the alphabet. What have y'all got going on today, huh? Okay. So, here's the first part of the problem. X squared times, we're doing example 8, bottom of page 148, chapter 2, differentiation, 2.5, implicit differentiation, bottom half of page 148. Last example in this section, 2.5. So we're looking for a tangent line. Okay, that's what we're looking for. Find the tangent line to the graph of this thing is equal to y squared. Okay? At the point, root 2 over 2, root 2 over 2. Okay, I'm still getting used to these reading glasses. They sort of freak me out sometimes. Because I hadn't worn glasses for more than 9 years since they fixed the other eye. And then they fixed this one. I have to go back to glasses again. All right. Now, I'm going to tell you something I would do to make this a little easier. Does anyone know another expression for root 2 over 2? It means it has the same value, but it just is a different way to express it. No, okay, yeah, don't enter any pi's in this. It has to be the same value. That's the same as 1 over root 2. 1 over root 2. Isn't it? Because if you rationalize the denominator, multiply the numerator and the denominator by root 2, that becomes root 2, and this becomes root 2 times root 2, which is 2, okay? To me, this is an easier form, at least for the first thing I want you to do. Verify that's in the curve, okay? Verify that point is on the curve. And you could have done it with that point, but this is so much easier, because all these are squared. What is 1 over root 2 squared? 1/2. And that is 1/2 again, and this is 1/2 again. 1/2 plus 1/2 is 1 times 1/2 is 1/2, and 1 over root 2 squared is 1/2. So 1/2 is equal to 1/2. Yes, that point is on that curve. I just like to verify that because I don't want them to give me a problem that's impossible to do because the point's not even there. But it's there. They wouldn't have done that with it. Okay? Now we need to find the tangent line. What 2 pieces of information do we need to have to find an equation of a line? There's several choices you can make here, but you need 2 pieces of information. A what? A slope. If we had a slope, that would be great. What else do we need? Slope alone won't do it. Good first start. You need one other piece of information. Well, an intercept would be fine. You don't have to have an intercept, though. You could have any point. See, a slope just tells you that could be anywhere. If it's that point, that's the line. Okay? So you have to have a point and a slope. The other 2 pieces would be 2 points. Well, we're not going to get 2 points out of this one easily, but we got 1 point already, so now all we need is a slope. How do we get a slope? Jesus answered. Take a derivative, of course, because the dy dx is your slope. So let's do that. Ooh, the first one is a what? Left-hand side. Second? How do you get that? Okay. He just wants to say negative, I think is all. Yeah, okay. Now, number one, everything's squared here, so how can it possibly be negative? Okay, so, what's that? Okay, all right. Oh, are you wanting to multiply those across? You can do that. In fact, that's a perfectly okay. Let's do it. So this would be x to the fourth is what you meant to say, right? Yeah. Plus, it's not going to help you a lot, but I thought.
X squared times y squared.
Okay, wait. Okay, now I think he's backing up and doing something else. He's doing a. Huh? Okay. He's doing a product rule. And you see, even if we multiply through, you're still going to have to do a product rule. So why do extra work to get to the same place? So let's go back, and I hope that's what he was meaning, because this is a product. It's the product of x squared times x squared plus y squared, right? So let's do the product rule. That's what you were saying, right? Say yes. All right, good. All right. Oh, you were wanting to multiply it out too? Oh, man. Okay, we can do that, or we can do the product rule now. If we multiply it out, we're going to have the product rule still to do. Product rule? Say again? I think this is. Okay. How do we do the product rule? Okay. Okay, x squared, that's the first, times the derivative of the second. What's the derivative of the second? 2x plus 2y, missing one little thing, y prime. Right. All right. And that's equal to? Oh, wait, we're not through. No, we did. No, we didn't. Okay, wait. You're confusing me now, aren't you? Okay. Trying to get me off track here. All right, that's just the first part of the product rule. The first times derivative of the second, what's the second part of the product rule? Plus 2x times x squared plus y squared. Okay? Now, you've taken derivative of the left-hand side using the product rule. How about the right-hand side? You may have said it. I can't hear that. 2y dy. Okay, I'm just going to write y prime. That's a little easier. Okay, now what do we do? Yeah, before we figure out like terms, we've got to do some distributing first. So let's distribute first, and what will this be? First term will be what? 2x cubed. Oh, bottom part of the alphabet is finally coming in strong here. Rita is here. And we got 2 of the bottom of the alphabet. Top part is perfect attendance. Okay, next. Plus 2x squared y prime. Good. Plus 2x cubed. This is example 8, bottom of page 148, chapter 2, differentiation, 2.5, implicit differentiation. Okay, 2x cubed. What's next? Y squared. And then we'll leave the other side alone for now, 2y prime. Now we've got everything done there. Now we can combine some like terms. I only see 2 that we can combine. What are they? Your 2x cubed. So let's get those. What would that combine to? 4x cubed plus 2x squared y prime plus 2xy squared equal to y prime. Now what? Get out of there. Say again? Do something to the x. Is that what you said? What did you say? Okay, there's no parentheses, so there's not much to distribute here. Distributing is multiplying across parentheses. Okay, like we did that. Okay. What do we want to do now?
You said we can't distribute the X to my.
What do you mean by distributing the X?
Because I was thinking like the FOIL method when I saw that, so I was like, we always just put parentheses and put out the X.
Okay, you're going to factor out an X, is that what you mean? Okay, you could do that. Not going to help you a lot, but you could do it. It's a legal move in most states. Okay? But what could you do? I mean, what do you want next? What are we gunning for? Remember, let's not lose the forest for the trees here. Yes, we want to get a prime by itself. We're looking for that derivative. So what are we going to have to do? Okay, divide by 2x. 2. Okay, now that is something that would be a very nice thing to do. Let's divide everything by 2 so we eliminate all those numbers, or a lot of the numbers. So this becomes a 2, that disappears, that disappears, that disappears. Good idea, okay? All right. Good deal. Now that's not a bad idea to do. But now let's get back to we wanting to isolate the y prime. So the first thing we got to do is get them all together. So what are you going to do it? Subtract what? Okay, you could do that if you wanted to, then you got to subtract these and get them over there. Let's subtract this one and get it over here with that one. I like that idea. So this is a minus x squared y prime minus x squared y prime. Okay? Now I'm going to need more room. Okay? So what I'm going to do is come up to the top here and write down what we've got so far. 2x cubed. These go away. Plus xy squared is equal to y prime minus x squared y prime. Feel like I'm stuttering, okay? And this is a squared here that did not print, okay? Right? Yeah, okay. Now what next? Your idea about x down here is a pretty good idea up there, except not for x. What is the goal? Don't forget your goal. Yes, get that y prime by itself. So what do you got to do? Putting it all on one side of the equation was for the sole purpose of isolating. Factor it out. You're factoring, okay? So this is going to become y prime times what's left. Now you're undistributing, factoring. Y minus x squared y. He's real tempted to pull the y out too, but we don't want the y. We want the y prime by itself. So now what do we do? Divide both sides of the equation by this y minus x squared y. Okay? The other side of the equation is over here, and this is going to get ugly. Y minus x squared y. Okay. Now I need some more rooms. Get out of there. Okay. So let me come down here maybe and write what we've got now. Okay. I was dividing by that, but I don't see my dividing line. There it is. Okay. These go out now. So now we have the y prime is equal to, oh, this is messy over here, but hopefully you see it. Now I'm going back to Ryan's idea of factoring out the x up here, just in the numerator. So that's going to have an x in it. x times 2x squared plus y squared. Okay, my pen's writing slow, so things are getting a little jumbled here. Okay, divided by y, because you can factor y out there, and that leaves you a 1 minus x squared. Now, there's nothing gained by factoring them out. It's just made it a little easier to write. Okay? There's your y prime. Okay, what does y prime tell you? Why are we getting a y prime? Second, it's a derivative, right? Why were we after a derivative? What does derivative tell you? Slope of what? At a point. And what point do we have? What's the point? That point. We want the slope at that point. We have the point, we need the slope at that point. Now, is this going to be easier to plug in when you put 1 over root 2? I think so. So let's go back and rewrite that. I erased it, and I want to rewrite it. That's the same as 1 over root 2. My pen is really slow. 1 over root 2. Because that's so much easier to plug in. Okay? So if it's okay, I'm going to erase my work down here. Is that all right? I don't think I need this anymore, and I sure need more space. Okay? I hope I didn't make a dumb error, because I'll never find it again, because I just erased all the evidence. Oh, that was clever, wasn't it? Okay, so let's plug this point in that expression. So y prime at 1 over root 2, 1 over root 2 is going to be what? Well, 1 over root 2 over 1 over root 2, the y over x is going to be, since they have the same value, y over x is, or x over y, sorry, 1. Okay, so forget about that one. So let's just do the parenthetical part. 2 times what? 1 over root 2 squared? We said it before. A little louder. 2 times 1 over root 2 squared. You're plugging 1 over root 2 in for your x. 1/2, okay? Plus 1 over root 2 squared is 1/2, okay? And this is divided by, the y's disappeared, remember, 1 minus, help me, 1/2, okay? So that makes our numerator 2 times, and 1/2 plus 1/2 is 1. 2 times 1 is 2, divided by 1 minus 1/2 is 1/2. And 2 divided by 1/2 is, anyone know what that is, or do you need to work it out? 4, exactly. Okay, it's 2 times 2 over 1, which is 4. So there's your derivative at that point. So now we have the slope and a point. How can we get the equation of the tangent line? We have a point and a slope. Yes? Second. Y minus.
The book got 3.
Y minus y1 is equal to m times x minus x1. The good old point slope formula. That's why we're looking for a point and a slope. Yes?
I believe they made a mistake. The book got 3, you got 4.
Oh my goodness.
Yeah, that's crazy, right?
So why did the book make a mistake?
I think where you got x, there's supposed to be like an intercept, like a point. Like you got 2, but I think it's supposed to be an intercept.
Okay.
2 over 2.
All right, let's see. Oh, let's see. I see. It's Not inconceivable. Okay. Oh. 2 times 1/2 was 1. Wait a minute. Okay. I erased the evidence, remember? So let's go back here. Okay. It's right here. Okay. I think we wiped out those, and then I messed up here. That parentheses is out of place. Okay? That's what the problem is. That parentheses is wrong. Okay? It should have been there because it's 2 times 1/2 plus 1/2. Well, 2 times 1/2 is 1 plus 1/2 is 3/2. So you're absolutely right. Good catch there. Okay? That's 3/2. Okay? Divided by 1/2 is 3/2 divided by 1/2. 3, okay, because the 2's basically disappear, and that's 3/1, which is 3. All right, now we got it. So let's continue. What's the equation of the tangent line? Y minus, now we could go back to the other if you wanted to. Square root of 2 over 2 is equal to 3 times x minus square root of 2 over 2. I'm not sure that's any advantage or not. Now, what you could do with that if you wanted to is distribute and make that 3x minus 3 root 2 over 2, and then add root 2 over 2 to that. I can't get my root 2 to write. Okay, and that would then produce 3x, and you got 3 root 2's over 2 plus 1 root 2 over 2. How many root? One's a minus, one's a plus. So it's what? Okay, negative 2 root 2 over 2. But then what could you do? Wipe out the 2's, right? So this will be 3x minus root 2. That's your y is equal to that. That's your slope. That's your equation of the tangent line in slope-intercept form rather than point-slope form. This, of course, is an answer, but it's just in not the most convenient form. Carry it on out, and you get it into the slope-intercept form, which is the most convenient. Same thing they got, right? Good deal. All right, homework exercises here. I gave most of these last time, but let me go through those again. Any of the odds, 5 through 19, they're all at Calc Chat. 5's at Calc View. Either 21 or 23, both at Calc Chat. 23's at Calc View. Any of the odds, 25 to 31, they're all at Calc Chat. 25's at Calc View. Either 33 or 35, they're both at Calc Chat. Isn't that my nose is itching? Must we go have company. I'll sneeze too. At some point. Both it does. Y'all awake? Okay, good. 33 or 35, they're both at Calc Chat. 33's at Calc View. Either 37, any of the odds, 37 to 41, they're all at Calc Chat. 39's at Calc View. 45 should be at Calc Chat, and 43 should be at Calc Chat also. Don't know if you want to do that, but you can if you'd like, or read it, or whatever. 45's at Calc Chat. 47's both at Calc Chat and Calc View. Any of the odds, 49 to 53, they're all at Calc Chat. 53's at Calc View. 55's at Calc Chat. 57's at Calc Chat. 59's at Calc Chat, and 61's at Calc Chat. You can do either 63 or 65. They're both at Calc Chat. And this is something that sort of gripes me about this author. I like this author a lot for all the additional stuff he supplies to you, but he has this sort of nasty habit of introducing new material in the homework exercise, okay? like we haven't even talked about orthogonal trajectories, except in the homework exercise. So you'll have to read that and figure out what they're talking about. But anyway, 63 or 65, they're both a CalcChat, and 67 is a CalcChat. 69 is another orthogonal trajectory, and that's at CalcChat as well. Oh, and then there's 71 at CalcChat. 73 is a proof for math majors. You might want to do that one. And 75 is a tangent line problem. 77, a normal line problem. And guess what? We haven't talked about normal lines either. So you have to read number 76 to get the understanding of what a normal line is. And again, why introduce new material in the problems rather than in the chapter? I don't know. All right. 2.6 is a very fun section, but I found in other classes we just typically don't have time to do it. It wasn't anything that was required in the course description, but it is a great thing, so lots of examples there. You can do them on your own, especially if you think that may be something of interest to you. But for right now, we'll stop right there, and let me give you your test on Chapter 2. Oh, if you need more practice problems, you can do either 3 or 5. They're at CalcChat. Oh, wait, I'm sorry. That was 2.8. Review exercises on page 161. You do either 1 or 3. They're both a CalcChat. 5's a CalcChat. 7's a CalcChat. Any of the odds, 9 through 19, are at CalcChat. 21 to 23 are at CalcChat. 25's a CalcChat. 27, any of the odds, 29 to 39, CalcChat. 41 or 43 at CalcChat. Any of the odds, 45 to 51 at CalcChat. 53's a CalcChat. Any of the odds, 55 to 65 are at CalcChat. 67 to 71 at CalcChat. 73 or 75 are at CalcChat. 77 is a CalcChat. Any of the odds, 79 to 83 are at CalcChat. 85 is a CalcChat. 87 is a CalcChat. Well, let's see. Any of the odds, 87 to, or 91, or not 89, okay? All at CalcChat. There's a problem-solving blurb at the end of the chapter. If you're interested in that, you can go for it. You don't have to do that, though. Then we'll be starting in chapter 3, which is the slide set I have up there. But let me first give you, goodness, that sneeze loosened everything up. Well, I don't think they're matter. Your test 2. Now, I think it's happened, what I asked not to happen. I haven't checked for sure. I believe there's still a few folks that haven't turned in test 1, and here I'm giving you test 2. So if you haven't turned in test 1 yet, please get it in as soon as you can. I think most of you, if not all of you, have turned in test 1. What's that? And certainly with only one page here, you're going to have some additional paper to write. Because remember that I need to see work. I can't just take an answer. Correct answer by itself only gets you half credit. So show work. That means you're going to need to attach some pages. All right. Any questions? Chapter 2. All right. Let's get started in Chapter 3 then. I'm going to clear this slide. Any questions on this one before I erase it?
So like derivative answers, we can't just give you an answer. That's a problem.
You can, and you'll get half credit for it, if it's correct. Okay? If it's not correct, you don't get half credit for it. Okay? So I need to see your work. Okay? It doesn't have to be a lot. If something's really obvious, yeah, 2 and 3, 2 especially, you could just write down the answer, because what more is there to show than what the derivative is? But some of the others, a lot of the others, you're going to need multiple steps. Any that you need multiple steps, be sure you show all your steps. Okay? I'll leave it that way. Some of them are going to require a lot of showing. All right, let's go back to the very first of this. Here we go. Chapter 3 is application differentiation. Chapter 2, we learn how to differentiate. Now we're going to apply the differentiation. The related rates were a part. That should have almost fallen here, but these are a little more specific things. So the first application is finding extrema. What do we mean by extrema? Another way to express that is extreme values, which means highest value or lowest values on some interval. So that's what 3.1 is going to be talking about. Well, first understand the definition of extrema of a function on an interval. Sort of what I was just arm waving about. Number 2, understand the definition of relative extrema of a function on an open interval. So we got to talk about open and closed intervals. And that leads to find the extrema on a closed interval. So that's all we're going to do in 3.1. Okay? So what in the world do we mean by the extrema of a function? By the way, I take it that this must be of Greek origin because the plural in many Greek words is an A. Okay? Extreme would be singular, not extremes, but extrema would be plural. Alumna, alumnus is singular, alumna, plural. Okay, so the A at the end. Minimum, minima. Maximum, maxima. Okay, I think that means they're from Greek origin. Okay? In calculus, much effort is devoted to determining the behavior of a function f on an interval I. That's where we're going to be putting a lot of emphasis. What is the function doing over this interval? Does the function f have some maximum value on I? Does it have a minimum value on I? Where is the function increasing? Where is the function decreasing? That kind of stuff is what we're going to be focusing on. In this chapter, you'll learn how derivatives can be used to answer those questions. In pre-calculus algebra, what you had to do was plot points and see if they were increasing, decreasing, and see if they reached the maximum, and it was sort of hard to do. Calculus came along, in fact, that's why Isaac Newton developed it, to make it a lot easier. Remember what I've said about good mathematicians? A little lazy. Always trying to find the best, the easiest, the simplest way to solve a problem. Calculus did that for me. It made it much easier to determine this kind of stuff. You'll learn how derivatives can be used to answer those questions. You'll also see why these questions are important in real-life applications. Okay? So here's the definition of an extrema. If f is defined on some interval containing some point c, somewhere in that interval, that's a value for x in that interval. Number 1, f of c is the minimum of f on that interval I, when f of c is always less than or equal to all the other f values in that on that interval. Now the f's are your y values, right? Okay, so this is the very minimum y value on the interval. Okay, there may be more than one of them, but it's the least. That's what we mean. It's the minimum of f on I when it's less than or equal to all the other y values on that interval. Okay? F of c is the maximum of f on I when f of c is greater than or equal to all the other y values on that interval for all x's in that interval I. The minimum and maximum of a function on an interval are called the extreme values. That's one word for it, or extrema. That's the singular form for extrema is extremum. Okay? Again, Greek. Okay? Minimum, maximum, minima, maxima. There was a trivia question at one time. Most car names, before they started just making up words, were all singular except for one. Anyone think of which name of a car, not maker of a car, but name of a model of a car is a plural word? The Maxima, exactly. Why did they choose it? How can one car be more than one Maxima? I don't know. Never mind. Okay. So anyway, the function, it's called the extrema, the minimum and maximum value of the extrema of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and the absolute maximum. Because on that interval, you can't get any higher or any lower, so it's the absolute maximum or minimum. You may have more than one, but they're going to have the same values. Or the global minimum and global maximum. That's another way to express it, okay, on that interval. Extrema can occur at interior points or at the endpoints of the interval. Now, what do we mean by an interval? If you're going from -7 to +9, okay, that means on that interval, -7 to +9, whatever the maximum value and minimum value of the function, whatever the function is doing in there, that would be what you're determining. Now, the endpoints could be, if that's a closed interval, okay, you're including -7, you're including +9, then you have to consider what's going on here, everything in between, and here. So it can include the endpoints. The endpoints are sort of a pain in the neck, but you have to do it. Extrema that do occur at the endpoints are called endpoint extrema. Wow, what an incredibly creative name that is. Okay. A lot of this is just terminology, and you might wonder why. Well, we'll be talking about this the whole chapter, so you need to know what we're talking about. Okay. Now, a function need not have a minimum or a maximum value on an interval. Well, that seems hard to believe. For example, in this illustration here, the interval is from -1 to 2. Now, if you included the endpoints from here to there, including the endpoints, that's going to be your maximum. Of course, your minimum is down here. Okay? But if you did not include the endpoints, so these were open circles like this, you still have that minimum here, but they do not have a maximum. Okay? Because you see, this implies you can get closer and closer and closer to 2, but just not equal to. And so you can't ever say, well, that's the maximum value. Because however close you get to 2, but not reaching 2, I can get closer. Okay? Because if that is 1.999999999, then I can get closer and do it 1.99999999999. Okay? That's even closer. So you can't say there's the maximum value, because you can get closer and closer without ever reaching 2, okay, because it's not included, but you can get arbitrarily close. So no matter what number you said, I can give you one that's closer. So it's a continuous function on -1 to 1. Okay. When you include the endpoints, you put the brackets. Are y'all familiar with that? Brackets mean it's a closed interval. You're including the endpoints. If you have parentheses, that means the endpoints are excluded. You're not including the endpoints. Okay? So this function here has a minimum and a maximum on the closed interval, but does not have a maximum on the open interval. It's approaching 2, but not getting there. Okay? I mean, as x approaches 2, this is approaching 5, but never, ever, ever reaching 5. But getting closer and closer and closer to 5, so it doesn't have an absolute maximum. Okay? Does that make sense? Again, you're probably saying, why? What does it matter? Okay? Doesn't a lot, but a little bit. Okay. Moreover, in this figure, the C part, now it doesn't have a minimum. If this function is not defined, well, no, I'm sorry, don't say that, is redefined, that your g of x here is redefined define that at g of 0 and x equals 0, this has a value of 2. Okay? Well, that's no longer a continuous function. G is not continuous because it has a hole in it right there and jumps up to here. Okay? Now, that's a removable discontinuity, but it is still discontinuous. Okay? So since it's discontinuous, you've lost your minimum. You can get closer and closer here, but you never reach that value, I think, of 1. Okay? Now your maximum back because you included the endpoint here. Okay? You made it a closed interval, so you got a maximum back, but now you lost your minimum. Okay? If this was an open interval here, you don't have a maximum or a minimum. Okay? For this particular function. Okay? The continuity or lack of continuity can affect the existence of extrema on an interval. Believe it or not, that's sort of the magic we're heading toward. So here's a theorem that all this sort of suggests. If f is continuous, now here we're saying f has to be continuous, on a closed interval, a to b, then it guarantees that f has both a minimum and a maximum on that interval. If this is open interval, you don't have that guarantee anymore. If it's not continuous, you sure don't have that guarantee anymore. But if it's continuous on a closed interval, f has to have both a maximum and a minimum on that interval. Okay, make sense? You might be saying, so what? Okay. Now, let's now talk about relative extrema. We were talking more about absolute or global extrema. Let's talk about relative extrema. And this is going to lead to the concept of critical numbers. So that is really where this is heading. That is, your applications of derivatives is going to be producing your critical numbers. So we'll get there soon. In this figure, the graph of f of x is equal to x cubed minus 3x squared has what they call a relative minimum at this point 0, 0, I mean maximum, okay, and a relative minimum down here at 2 minus 4. Now this is just looking at the graph. Why do they say relative? Because you notice this doesn't say what interval you're talking about, so this is going on and on and on. Well, guess what? This is heading to negative infinity and never going to turn around. So this doesn't have an absolute minimum. This over here is going to positive infinity, never turning around. So it's not going to have an absolute maximum because this is a closed interval. This is not even an open interval. This is from negative infinity to infinity. That would be open, I guess. Okay? But right here, anywhere around this point here, there's the maximum value. So we call that a relative maximum. Anywhere around here, that's your minimum value. So you're not going over here to get those that are less. You're not going over here to get those. You keep your interval small enough, that's a relative maximum. That's a relative minimum. And formally, for a continuous function, you can think of the relative maximum as occurring on the hilltop and the relative minimum as being at the bottom of the valley. Okay? If it's a continuous function, that's one way to think of it. Okay? Those are relative minimum because there is no absolute, because this is an open interval that happens to be going forever, and this is never going to turn around and come back up. This is never going to turn around and go back down. Your end values are going to infinity. Okay? Make sense? Okay. Such hill and valley can occur in two ways. When a hill or a valley is smooth and rounded, the graph has a horizontal tangent at that high point or low point. Okay? Let's think about that. Let's think about the tangent line here. It's pretty steep here, right? But then the closer you get to that hill, relative maximum, your tangent line is decreasing until, as long as that's smooth, at this point it goes to 0. The slope of the tangent line goes to 0, And past that, it's going to be negative. It's going downhill. And it's going downhill pretty quickly here until you get close to this point, and now the negative value is actually increasing, becoming less negative gradually until it goes to 0 and then goes positive again. So wherever your first derivative is 0, if you've got a smooth function, and this was smooth, rounded, okay, then you have first derivative going to 0 at your endpoints. There's a key, a really big key. However, when the hill or the valley is sharp or peaked, okay, then the graph represents a function that is not differentiable. Because if you have a sharp point there, the derivative here is one value, derivative here another, there is no 0. There's no limit to the, on either side. They're going to different numbers. So then you have like your absolute value functions and those kinds, not going to happen. But you still have a maximum or a minimum there. When the hill or the valley is sharp and peaked, the graph represents a function that is not differentiable at the high point or the low point, okay, because the derivative doesn't exist there. When it's smooth, the derivative is 0. When it's not smooth, it's one derivative this way, another derivative this way, near this way to meet, okay? So here's the definition of relative extrema. Now, if you've been wondering why they picked up that letter C to mention as a value somewhere on the graph in that interval, we're going to get to it pretty soon. Okay, not quite yet. We're going to get to it soon. If there is an open interval containing some number C on which f of C is that maximum value, okay, open interval, containing C in which f of C is that maximum value. The endpoints, well, no, the endpoints are open intervals, don't matter anyway. C is your maximum, okay? Then f of C is called the relative maximum of f, or you can say that f has a relative maximum at C f of C. If there's an open interval containing C on which f is a maximum, then that's called a relative maximum of f wherever your function is, not just that little interval. If there's an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum of f, or it has a relative minimum at C f of C. The plural of relative maximum is relative maxima. The plural of relative minimum is relative minima, as if you really care. Okay. The relative extrema, maximum or relative minimum, are sometimes called the local maximum or local minimum. The absolute maximum minimum, global, they have other names for it. Relative is local maximum or local minimum, meaning in the locality close by, those are the max or min. All right. So it says find the value of the derivative at each relative extreme shown here. Okay? So we've got to find the derivative. Okay? Now, how are you going to find the derivative of that? You have one or two ways to do it. Quotient rule, or you could have written this as 9 times x squared minus 3 times x to the minus 3 and then use the product rule. Either way you want to do it is fine. Okay? So someone wanted to do that fairly quickly. Okay? You don't have to do all that quickly, just do it. Okay? What would be your f prime here? Which rule you want to use? Quotient or product? I don't care. Quotient. Okay, I know y'all like that. How does that go? This is why you liked it. Low d high. Low is x cubed. D high is, why don't we go on and multiply this through? It'd be 9x squared minus 27. I don't, there's that numerator, rather than having it in two pieces, okay? What is d high then? Not that hard. 18x, is that what you said? Say yes, okay, 18x, okay. And what goes next? We did low d high. Minus high d low, which would be your 9x squared minus 27 in parentheses. And what's your d low? What's your d low? 3x squared. Okay. All over, throw things around, see if I care. All over x cubed squared, which would be x to the 6th. Right? All right. Now we need to distribute in our numerator. And that will be 18x to the 4th. That's the only term there. And here we have a minus 27 x to the 4th. And then we have a minus, which is plus 81 x squared. All divided by x to the 6th. Now, anyone think of anything we might do here to simplify? In the numerator, you certainly can. Okay. Not going to help you a lot, but it might do some. Say again? Yes, how many can we get rid of? 2. So let's make this x to the 4th. This will make this x squared, and this will be 81. Still want to factor out the 9 too? Okay, it's fine. 9 times 2x squared minus 3x squared. We should combine those like terms. Why didn't we do that? I'm not sure. Y'all are crazy. Okay, never mind. Okay, plus 81. No. Plus 9. Okay. Forgot what I was doing. Over x to the 4th. Okay, let's combine those two. That would be minus, I'm going to go and multiply, well, no, I'll leave the 9 out here. Okay, 9 times 9 minus x squared. Is the numerator, there's your denominator. Okay. Now, find the value of the derivative at each of the extreme values shown. They told you 3, 2 is your extreme value. Okay? So we want the derivative, what we have just found, when x equals 3. So what does that give you when x equals 3? There's your numerator over there. 9 times 9 minus x squared over x to the 4th. When x is equal to 3, what's your derivative? Not that hard to do. Plug in x equals 3 in that numerator. Say again? Plug in 3. Oh, 3, yeah. Well, that's the value. X equals 3. What would be your derivative? So, 81 minus. Okay, wait. Go multiply the 9 through on the first, you got to do the second one too. Why don't you just leave the 9 out here and just plug in the 3 there? 9 times 3 squared, minus 3 squared. Is what? Is what? 9 minus 3 squared.
Oh,
3 squared is 9. 9 minus 9 is 0. Doesn't matter what you multiply there, no, what you divide by 81, guess what? The numerator is 0. So your Derivative here is 0, meaning you have a horizontal slope, which is what we were talking about before. So the f prime of 3 is equal to 0. Okay? How about f prime here? Well, this is your absolute value function. I don't know if you remember how we define that. It's defined as a piecewise defined function. This is it's minus x anytime x is less than 0, and it's x anytime x is greater than or equal to 0. Okay? That's how we define f prime. Absolute value of f. Because if x is a negative number, negate it and make it a positive number. If x is a positive number, that is your absolute value, right? That's absolute value. So what's the derivative of this when x is negative? What's the derivative of minus x? Is what? Derivative of minus x.
Is it -1?
Negative 1. What's the derivative of positive x? Positive 1. So what is the derivative of 0, 0? It doesn't have a derivative there. It's minus 1 on this side, positive 1 on that side. It is not defined. F prime at 0 does not exist. Right? Okay. Now, let's head over here to this one. F of x is equal to sine x. What's the derivative of f of x? Help me, somebody. Say again?
Sine x.
Derivative of sine x.
Cosine.
Say again?
Cosine.
Cosine x. And what is cosine when x is equal to pi halves? Cosine of pi halves?
Say that again.
Cosine of pi halves?
Cosine 9x.
No. Cosine of pi halves. That's your relative maximum at pi halves 0. What's cosine, which is your derivative of sine, at pi halves?
0.
0. Okay? Down here at 3 halves pi. What's your cosine of 3 halves pi?
0.
0. So here on this one, because this is a smooth, continuous function, this is not smooth. This has the derivative f prime at pi halves is 0, and f prime at 3 halves pi is 0. So your derivatives are 0 on smooth curves. On non-smooth curves, the derivative doesn't exist. Okay? So, that's your relative max here, your relative min there, relative min max and relative min there. Okay? All right. We just did example 1. I didn't realize that was example 1. Okay? We just did example 1. I didn't write it out for you. I was just thinking, I didn't pay attention to the example at the top. I just thought they were showing this as part. So any questions on example 1? Let's see how they did it. Derivative of the first one, as we did. They did a quotient rule. Okay? They did low, D high, minus high, which is this thing, D low, which is that one, over low squared, or low low. Okay? There's a differentiation, working that out. They skipped a lot of steps, didn't they? Is 9 minus x squared over x to the 4th. They skipped a bunch of steps. I mean, just about all the steps, except the final. Don't do that on your test, okay? At the point 3,2, which they told us was your relative maximum, the value of derivative is f prime at the x value, 3. And when you plug 3 in here, 9 minus 3 squared is 9 minus 9 is 0. No matter what the rest of that's doing, it's 0. Okay? So sure enough, your first derivative is 0 at the maximum point. The B one, at x equals 0, which is your minimum point, relative, it's the absolute minimum, they call it a relative minimum, but it's actually absolute minimum. The derivative of that does not exist, because on the left-hand side that's a -1, on the right-hand side that's a +1. F prime does not exist at 0. Okay? Of the limit. They did it this way. I did it by the definition. It becomes -1 from the left, +1 on the right, never the twain to meet. On the third one, the derivative is cosine x, and at the relative maximum here, pi has 1, your cosine is 0. At the relative minimum there, at 3 has pi -1, your cosine is also 0. Okay. That was example 1. All right. Before we go to example 2, before we go to the next page, anyone in favor of a bladder break? All right, let's take a quick break. I'm certainly in favor. That's why I brought it up. Notice we... All right, so if you think back of example 1, that smooth curve that we had to begin with at 3,1 or 3,2, whatever that one was, the absolute value that didn't have a smooth curve, and then the sine function that had 2 smooth curves. Each relative extrema, minimum or maximum, the derivative was either 0 or did not exist. The x values at these special points are called critical numbers, hence C. That's why they named that point C. Okay? And this figure illustrates 2 types of critical numbers. The first, where the derivative doesn't exist, f prime of C does not exist, because f prime of C here is getting sharper and sharper and sharper, going to positive infinity. It looks like this way. Going this way is going to, starting at negative infinity and getting slightly less. Function, the first derivative doesn't exist there. Function exists, first derivative does not. But if it's a nice smooth curve, then you have a horizontal tangent line, so there your derivative is 0. Both of these are critical values where you have your extreme values. Both of these happen to be maximum. Okay? Make sense? All right. So here then is the definition of a critical number. Let f be defined at some number c. So f has to be defined at that number c. If f prime of c is either 0 or f does not differentiable at c, in other words, the first derivative of f does not exist there, then c is called the critical number of f. That's it for a critical number. If the first derivative is 0 or doesn't exist at that point, then c is a critical number. Remember that. That's the points we're going to be investigating. Notice that the definition above, that the critical number c has to be in the domain of f. Okay? And it's defined at c. But c does not have to be in the domain of f prime. And we saw that in that peaked example, in the absolute value example. It doesn't have to be in the domain of f prime. So here's theorem 3.2, which follows pretty quickly. Relative extrema only occur at critical numbers. If f has a relative minimum or a relative maximum at x equals c, then c is a critical number of f. Okay? If f has a relative minimum or a relative maximum at x equals c, then c is a critical number of f. Okay? So another sort of definition. Yeah, this is expressed as a theorem. Okay. Now, there's a little blurb here on Pierre de Fermat. sort of an interesting character. He was trained to be a lawyer, but don't take that against him. They had, no, I won't go into that. But mathematics was sort of a hobby of his. But he was incredibly good at it, okay? And he communicated with a lot of the famous mathematicians of his time, and he was well respected and recognized as a brilliant mathematician, even though that wasn't his chosen profession. He was a lawyer, okay? So an unusual character. One of the, this theorem 3.2 is attributed to Fermat. In one of his letters to, in fact, one of his very last letters he wrote to his friends, they mentioned here, he was always writing, bouncing mathematical ideas off of their heads, you know, and stuff. He said, "Oh, I've come up with this great proof for this theorem that no one had been able to prove yet. It really turns out really nice. I want to show it to you when we get together." He died. They never got together. He had made some just sort of sketchy type comments in the margin of the page, but no one could ever find his theorem. And it was called Fermat's last theorem, okay? This was one they found, but it took, I don't know, into the present or last century. He was 1600s. It was in the 1900s where they finally proved his theorem, that he had found this proof. They don't think any way possible that he could have done it the same way we did it in the 1900s, because we had to use computers like crazy then, and he didn't have them. But he claimed he had the proof of it, and so said, "I'll have to show it to you next time. You know, it's too much to write on the page. I can't wait to show it to you," and no one could ever find it again. Okay, so anyway, interesting character. Potential paper topic if you're interested in that, or his famous last theorem. So, find the extrema on a closed interval, okay? The theorem 3.2, which was this one, if F has a relative minimum or relative maximum at x equals c, then c is a critical number of F. Notice those are relative minimum and relative maximum, okay? That states that relative extrema of a function can occur only at the critical numbers of the function. Knowing this, you can use the following guidelines to find the extrema on a closed interval, okay? So here we have a closed interval. This time you're counting the endpoints. So what's going to define the extrema on that closed interval? Well, they could be a critical number, okay? Because that's going to be a relative maximum min. So to find the extrema of a continuous function, it needs to be a continuous function on a closed interval a to b. Here's the steps. Pretty easy, I find the critical numbers. How do you find the critical numbers? What's a good use of answer? Take a derivative, okay, and then you do what to the derivative? Either set it equal to 0 or identify where it doesn't exist. Okay? Two things. If you do those two things, you found the critical numbers at a to b. Now this is, you're trying to find the extrema on the closed interval a to b. This will give you the critical numbers on the open interval a to b. Okay? So those are potentials because every one of those is going to be a relative extrema, a relative extreme value. May not be the extreme, but it'll be a relative extreme. Evaluate F at each critical number. Okay? So you've got the first derivative. You see whether it's either 0 or doesn't exist. That's the first derivative. Then evaluate the function at each of those values. Okay? See what it is. Evaluate F at the endpoint, at the left-hand end, A, and at B, and then the least of those values, the F value at the critical numbers, here, 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 okay? And at the endpoints here and here, one of those, the least of those is going to be the minimum, the greatest is going to be the maximum. Blah, blah, blah here. Let's actually do it. Find the extrema, the absolute extreme values of f of x equal 3x fourth minus 4x cubed on the interval from -1 to 2. How would you begin? One of those questions. Okay, we are going to do that at some point. You want to do it now, that'll be fine. Let's plug in -1. So f of -1 is, work it on out, 3 times -1 to the 4th power minus 4 times -1 to the 3rd power. Okay? A little louder? Okay. What is -1 to the 4th power? +1, so that would be 3. And what's -1 to the 3rd power? -1 times -4 is +4, so that would be 7. So we found the left end value. How about the right end value? F of 2 would be 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. What would that be? 3 times 2 to the 4th. A little louder. Second? That's to the 5th. Second? 2 to the 4th. 16. All right. Here's the way I think of it. May not be the best how to do it. It's 2 squared times 2 squared. What's 2 squared? 4 times 4 is 16. Okay? Minus 4 times, what's 2 cubed? 8. Okay? So this would be, what is 3 times 16? Anybody? 48 minus 4 times 8? 32. And that's equal to 16. All right. So we got our 2 endpoints. Okay? So we either have to get something less than 7 or something greater than 16 in between. So how do we find the in-between values? Second? Take a derivative. Excellent answer. Okay, so f prime of x is equal to, what would that be? (12x to the cubed minus 12x squared). Okay? And then what are we going to do with that? Second? Okay, yeah, we can do that. We can actually factor out a 12x squared, and that leaves us x minus 1. Okay? There's your first derivative. What do we want to do with that? Okay, we'll start here. Find the critical numbers, right? And where are the critical numbers? Either where the derivative is equal to 0 or the derivative doesn't exist. Okay? So that's what we want to do. Is there any place in the world where this derivative does not exist? Any value for x for which it doesn't exist? None. It exists everywhere. So rule out that doesn't exist. Where would it be? What do you look for to find out where it doesn't exist? If you see a variable in the denominator, anytime that could become a 0, the denominator could become a 0. This has no denominator, so those are out of the question. Another one would be anywhere you have the possibility of a negative square root. This has no square root, so that's out of the question. And the other one that we know about so far is anywhere where the log could be either negative or 0. This has no logs in it. Okay, so this is a polynomial function, perfectly defined everywhere. So there's no place where it doesn't exist. Are there any places where that derivative is equal to 0? Any values for x? Set it equal to 0. So x equal 1. Any others? X equals 0. Okay, 2 places. So now we evaluate f, not f prime. We know what f prime is, 0 there. We evaluate f at these 2 values, your critical values. This is C1, this is C2. 2 critical values. Okay? So let's do f at 0. What does that give us? Say again? 1? As I keep hearing 1? It sounds like a 0 to me. 3 times 0 minus 4 times 0. 0 minus 0 is 0, right? I think you were doing the other one. F at 1, on the other hand, would be what? Really? It's 3 times 1 minus 4 times 1, which would be negative 1. Okay. Now, which of these is your minimum value? Okay, that's where this is your minimum. How about your maximum? Your f at 1, whose value is minus 1, that's your minimum value. So minimum at 1 minus 1. Okay? Your minimum y value is minus 1. How about maximum?
16.
At 16, so that's the max is at the point 216. Okay, the maximum value is 16, okay, but it's at the point 216. Minimum value on that interval, negative 1 to 2, would be at x equal 1. The value for y would be minus 1. That's the minimum y you get, and it'll be at the point 1 minus 1, of course. Okay.
Is this the only way you use extremely just to find minimum and maximum numbers?
Is this the only what?
Only way you use extreme to find minimum and maximum values?
Okay. We're going to learn a few other techniques that will help finding these. Right now, it's the only one we have in our tool belt now. We'll find others that work better a little bit later, but we're going to build on it. When we get second derivatives, that's going to help us find them even faster. This finds them, but that will find them faster. Okay?
Will you use extrema after calculus 1?
I'm sorry?
Will you use extrema after calculus 1? That's
Oh, yes. I mean, any of you might ever go into a business, you think? Anything, time you might want to maximize profit, say? Any kind of business. If you want to maximize profit, that's an extreme, right? First derivative. Okay. All right. You may not actually do it, but you are looking for that kind of thing. Want to make the best return on stock? Well, we won't go into all that. Okay. So here's what they suggest. They differentiated first rather than doing the endpoints. It doesn't matter. They wrote this down again as a creative idea. Then they took a derivative and got the same thing we did. Then they wanted to set that. Okay. To find the critical numbers of f in the interval negative 1 to 2, you must find all the x values for which f prime of x is 0. These glasses I can't read. This is f here, this is f prime here, is 0. And all the x values for which f prime doesn't exist. This thing All right, we haven't taken the derivatives yet. I thought we did. Okay. No, that is the derivative. That is the derivative. You set that equal to 0. That's going to give you some. Look at that thing. Is there any place that doesn't exist? No, that exists everywhere. So there's not going to be the second case where it doesn't exist. So factor that, and you get 12x squared times x minus 1 equals 0. This gives you either x equals 0 from this factor or x equals 1 from that factor. Those are your two critical numbers. So we're going to evaluate f at those two values. If there was some place it didn't exist, evaluate it there as well. The first derivative doesn't exist. Okay? Because f prime is defined for all values of x, you can conclude that these are the only two critical numbers of f. Okay? And they're both in the interval plot. Oh, yeah, both in the interval. I didn't point that out to you before, but we got to make sure. If one of these had come out being 3, that's outside the interval. So you don't even mess with it. If one of them came out being -2, outside the interval. Don't mess with it. Both of these are within the interval, so we're okay. We will evaluate both of them. Okay? And then we'll do the left endpoint and the right endpoint. Left endpoint is -7, just like we did. -1 came out being a value of 7. Okay? At the first critical number, 0, came out being 0. So 0 now is a potential minimum value. This is a potential maximum value. But we go on to x equal 1, or x equal 1, our second critical number, and that gave you a -1. That throws f of 0 out of the picture. Can't be a minimum or a maximum. Okay? So this looks like it could be a minimum. Then you do f of 2, the right endpoint. That gets you up to 16. That wipes this one out. So there's your minimum. There's your maximum. And on a closed interval, the function will have guaranteed to have a minimum and a maximum. You could have more than one minimum, but they have to have the same value. Like that sine function we did, it has a maximum every, from pi hat x equal pi halves, and then added 2n pi to that, or subtracted 2n pi from that. Have lots of them that have maximum of 1 and minimum of -1. Okay? So you could have more than one, but those are your minimum and maximum values. Okay. Here's the graph. Glad they did it and not me, because it's a closed interval. We include the endpoints. Here's -1, 7, 0, 0, 1, -1, and 2, 16. Obviously maximum, obvious minimum. Okay. Now, there's some interesting things going on with this one. Notice here, this is neither a local or a, what is the other name for it? Relative maximum or minimum. It looks like it's going to be a relative minimum, but then it looks like it would have been a relative maximum. That's neither one. Okay? We'll get to that later. This, though, is a local minimum and the absolute minimum as well. Okay? This one got bumped from minimum by these two, bumped from maximum by that one. So it's neither. That's your absolute maximum. On that closed interval. Does this make sense? Okay. And then what I just said, noted in that figure that the critical number x equals 0 does not yield a relative maximum, minimum, or a relative maximum. So I want to go back quickly here, if I can do anything quickly. I think it was for Mott's, this one. If f has a relative minimum or maximum at x equals c, then c is a critical number. Okay? If it has a relative minimum or relative maximum at x equals c, then c is a critical number. Notice this doesn't go both ways. You can't say if c is a critical number, then it has a relative maximum or minimum there. No, it doesn't. That example we just saw says no, that doesn't happen. You found the critical number, you knew it was a critical number, but it's neither relative maximum or not relative minimum. Okay? So this one, if this is indeed one of Fermat's theorem, it goes one way but not the other way. This is, they have names for that too. Let's go back. They may, probably are going to get to say the same thing I just did. But this tells you that the converse of theorem 3.2 is not true. But just because it heads one direction doesn't mean it heads the other direction. That's what we mean by converse. Con means as opposed, like contrary, you know, the pros and the cons, the fors are against. Against, and versing is going. So if you're going one way, if this is true, that's true. Doesn't guarantee that if that's true, this is true. That means the converse is not true. Not always true. It may be true in some cases, but it's not always true. In other words, critical numbers of a function need not produce relative extrema. If it's a relative extremum in the interior, got to be a critical value, okay? But the critical number doesn't guarantee you're going to have a relative extremum. Whoa! Can it be that that's the last thing they do in the section? There are two more examples. Let's hit those. Let's see if we, I think that'll be our best place to do it. Example 3. Find the extrema of f of x is equal to 2x minus 3x to the 2/3, one of my favorite functions of all time, on the interval -1 to 3. Okay? Find the extrema. Extreme values. Absolute max, absolute min. Say again? Okay. Plug in the whole domain. Is that what you were saying? Please say no to that. The whole domain is an infinite number of plugins there. I don't have time for that. Which ones? The endpoints. Yeah, that sounds like a capital idea. Let's do that. Okay, so f of -1 would be, you tell me. I don't think so. 2 times -1 minus 3 times, and what do we mean by something to the 2/3 power? The cube root of -1 squared. Perfect. Or you could do the cube root squared. It doesn't matter. It comes out the same. 2 times -1 is -2 minus, and what's the cube root of -1 squared? What is -1 squared? 1. Cube root of 1 is? So -3 times 1 is? -3. So this comes out being -5. Okay, we have one endpoint value. Next. Alpha 3 is equal to 2 times 3 minus 3 times the cube root of 3 squared. I don't even want to think about that one, okay? What would this be? 6 minus 3 times the cube root of 9. Gonna have to depend on somebody having a calculator on that. Something a little bit more than 2, so this is going to be a slightly negative number. Minus
3 times the cube.
Oh, yeah, right. Okay. Okay, was I figuring badly? The
No,
cube.
I multiplied the 3 with it.
Okay.
The whole thing, 3
Okay.
times the cube.
Yeah, but the cube root of 9 is just a little bit more than 2.
Yeah,
Because
and then times 3.
okay, times 3 is a little bit, is just a little bit more than 6.
Yeah, 6.
And 6 minus, oh, did you just do, okay.
Yeah.
Okay, then do 6 minus that.
So negative 0.24.
Negative 0.24? Okay, that sounds reasonable. All right, that bounced the left-hand end from being a relative minimum. No, left-hand end could still be a relative minimum. Right-hand end could be a relative maximum. Are we done? Oh, let's find the derivative. What's f prime of x? 2 minus 2 over x to the 1/3. Interesting how he did that. Yeah, it's 3/2 times 3 would be 2, so it's minus 2 times x to the minus 1/3, which is over x to the 1/3. Okay. Now, why did we do that? You don't know. You're the one who told me to do it. Why'd you have me do that? You want to see me do it, okay? What are we looking for? Oh! What? What are we looking for? Either where the first derivative is. Second. I need to go back a few slides. If f prime, first derivative, is 0 or not defined, not differentiable or not defined, then it's a critical number. We're looking for our critical numbers. Okay? So, what do we want this to be? Second? Okay, if the first derivative is 0, is there any place that would make this equal 0? Any value of x would make that thing equal 0. Second? Oh, x equals 0, what happens there? Second? It's undefined. So x equals 0 is a critical number. So C1 will be 0. Okay? X equals 0, that's going to be undefined. Okay, but my question was, where is that going to be 0? Where is the first derivative going to be 0? X equals what? 1. You're absolutely right. So the other one is going to be C2 at 1. Now, those are the only two I can think of now that will be there. Now, let's see. It's between -1 and 3. Both of those numbers are between -1 and 3. So what do we do with those two numbers? Yeah, let's plug them into our f. So let's do f of 0. And what do we have? 0. Hey, that could be a maximum because both of those are negative. So you just bump this one out of the competition for good. It can't be a relative maximum or a relative minimum or absolute maximum or minimum. Okay? So let's do the second one, f of 1. And what will that be? 2. Help me. Minus. Say again? What's the cube root of 1? 1. 1 squared is 1. And 3 times 1 is 3. So what's that? -1. Okay? this one's out of the picture now. -5 is the minimum, and 0 is your max. Okay, I hope those aren't your profits. Okay, all right. So actually the best way to phrase that, the minimum is at -1 -5, okay, and the maximum is at 0, 0. Okay, let's see what they found. Minimum at f of 1 equal f of -1 equal -5, and at the critical number f of 0, 0, that's your maximum. Okay. Now, I just as soon not draw the picture. Sorry, people who are not here, you can't see what I'm going to hold up on the screen. You should be here. So here's the graph of that thing. Believe it or not, so far in this range, it never gets up above 0. It looks like it's heading there here. It may, but we're not there. At 3, you're still negative here. So here are there's your maximum there, your minimum at this endpoint. These are in between. I can't hold it up anymore. Weird looking thing, but you see where this one doesn't exist, x equals 0, the derivative, first derivative doesn't exist, then that happened to be turning out, that was a cusp where it comes up to a point, and that happened in this problem to be our relative maximum. Okay? All right, there. Need time to run to the second one? Okay. No questions? All right. Example 4. Now this one, for those of you who don't have a book, you can go to larsoncalculus.com and see an interactive version of this type of an example. Okay? And even those that do have a book, you can do that. Okay, find the extrema of this function. F of x is equal to 2 sine x minus cosine 2x. Okay. Oh, on the interval 0 to 2 pi. All right. Second, do 0 and 2 pi. All right, let's do it. F of 0 is equal to, what's the sine of 0? Absolutely, okay. Minus, what's the cosine of 0? 1, so that's a -1. Okay, could be a min, could be a max, we don't know. Continue. Continue. F of 2 pi. 2 times, what's the sine of 2 pi? 0 again. What's the cosine of 4 pi? 2 times 2 pi is 4 pi. What's the cosine of 4 pi? It's 1 again, so that would be a -1. Well, we have a tie here for either max or min so far, but we don't know which. Okay? So far. So what do we do next? Take a derivative. F prime of x is equal to 2 times the cosine of x minus what? It'd be positive. Okay, it's going to have a sine of 2x, but it'll have 2 of them, so it's going to be 2 sine of 2x. Everybody see that? Chain rule of the last part. That's where you get the 2k from. Okay? Now, what are we going to do with that? And how do we do that? Either where it's equal to 0 or where it doesn't exist. Do sines and cosines ever not exist somewhere? That's if they're in the denominator. Sine and cosine are functions that go on forever and ever and ever and ever and ever and ever and ever. Never. There's no place they don't exist. Sines and cosines, so you're good there. Just like a polynomial function. This has a tangent, a cotangent, a secant or a cosecant. Yeah, they don't exist in a bunch of places. But sines and cosines exist everywhere. Okay? So, the other option is, as Tarika was saying, is where it's equal to 0. So set this equal to 0. Now, what might be a good first thing to do? Divide out the 2's. Gone. Okay? So 0 divided by 2 is 0. Okay? Now, what would be another pretty good thing to do? Second? Well, we got sort of a problem here, don't we, Houston?
We have
two different trig functions. That's going to be hard to compare, aren't they? So what might we do? I'm going to leave cosine x alone. That's about as simple as I can get. But sine 2x, what is sine 2x? Anyone remember? Two, actually times sine x, cosine x. You're absolutely right. Okay, set that sum equals 0. Okay, factor out, is that what you said? Okay. All right, so factor out a cosine x, and that leaves what?
1 plus 2 sine x.
2 sine x. Okay, and that's equals 0. And then what do you do with this?
You can take them both.
Yeah, so each equals 0. So cosine x equals 0. Now, what values of x between 0 and 2 pi is the cosine 0? Pi halves is 1. X equal pi halves. And the other is 3 halves pi. And that's all between 0 and 2 pi. Okay? What do we do with the other one? 1 plus 2 sine x equals 0. Subtract 1 from both sides. That gives you 2 sine x is equal to minus 1. Then what? Divide both sides by 2. And that gives you sine of x is equal to minus 1/2. And where is that true? Between 0 and 2 pi.
That's where it's the third and fourth quadrant.
Third and fourth quadrant, you're absolutely right, because sine is positive in the first and second, and this is a minus 1/2. So it can't be in the first or second quadrant. So in the third quadrant, is sine negative 1/2 anywhere there? Where?
3 pi 6.
Okay, 3 pi 6 would be pi halves. Okay. Second?
3 pi over 5.
Okay. 3/5. Okay. All right. It's at your, okay. Think back. Okay. Your absolute value of this is 1/2. Okay. At what angle is sine equal 1/2? Okay, 3 pi over 2 is down here. But what value in the first quadrant is sine equal to 1/2? Say again?
We're talking about kind of like unicircle, right?
Say again?
Yeah.
We're talking about the unicircle, right?
Yeah.
It's pi
Well,
over
yeah.
pi over 6 is the pi
Any
over
angle will work. I mean, whether it's on the unit circle or 17 circle or not on the circle at all, where is the sine?
Didn't I say pi over 3?
Pi over what?
3.
No. Pi over 3 is at root 3 over 2.
So pi over 6.
Pi over 6, exactly. So you want to be a reference angle of pi 6. So in the third quadrant, that would be just past pi. So pi would be 6 pi, that would be 7 pi. So that would be at x equal 7 pi 6. 1/6 pi beyond here, that would be a minus 1/2. And where else? Quadrant 4, 11. 1/6 pi before you get to 2 pi, so that would be 11 pi over 6. All right, 4 places where, and then it's defined everywhere. So now we have 4 critical values. We need to evaluate the original function at each of those. Okay? So let's do f at, which one you want to do first? I really don't care much. Pi halves, why not? Pi halves. This will be 2 times the sine of pi halves minus the cosine. 2 times pi halves is pi. Okay? What is the sine of pi halves? Sine of pi halves. 1. Okay? 2 times 1 is 2. So this will be 2 minus what's cosine of pi? Second? Negative what? 1. Yeah, it is. So minus of minus 1 is 3. All right. So we have a new leader for a maximum. Still got a tie for minimum down there. Let's try another one. Which one you want to do next? 7 pi 6. Doing like the book is and take them in order. I kind of like to do that too. Okay, that would be 2 times, what's the sine of 7/6 pi? We just did that. That's negative 1/2, isn't it? Okay, minus the cosine of, and 2 times 7/6 pi would be 7/3 pi. Okay, that's going to take some head scratching. Well, 2 times negative 1 is, 2 times negative 1/2 is negative 1 minus. Now, what is the cosine of 7/3 pi? Well, 7/3 pi is, 3 will go into 7, 2, right? And 1/3 pi. So 2 pi gets you all the way back where you started, and the cosine of 1/3 pi. You do the sine of it. The cosine of it is 1/2. Yes. So that's minus a 1/2. Okay. So this is going to be minus 3/2. Right. So we just wiped out the 2 endpoints, haven't we? Because this is less than either one of those. Okay. Which one you want to do next?
11 pi.
Second. 11/6 pi. Okay. Oh, get out of there. So f of that would be 2 times the sine. We already know what the sine of 11/6 pi is, don't we? It's negative 1/2. That's how we got it. Okay, negative 1/2 minus the cosine of 2 times that. 2 times 11/6 pi is 11/3 pi. Ew. Okay, 11/3 pi, that's going to be past 3 pi, right? But 3 pi cosine is a negative 1, right? So cosine is positive 1 at the even pi's and negative 1 at the odd pi's. Okay? So you're past that, you're 2/3 pi past that. So it's a negative 1, and then another 2/3 pi gets you up to what? I think it's negative 1/2 again, isn't it? Huh?
I think so.
Okay, I think so too. Okay, so I think it's another negative 1/2. So this will be a -1 minus a minus 1/2. Last time was a 1/2, this time it's a minus 1/2. And that's going to be negative 1/2, right? So that's out of the picture. Okay? Because we've got one less than that, and we've got one greater than that. One more to go. Alpha of 3/2 pi. Okay, get it out of there. Now, 2 times the sine of 3/2 pi minus the cosine of 3 pi. Right? Because 2 times 3/2 pi is 3 pi. All right. What is the sine of 3/2 pi? Negative 1 times 2 would be negative 2. And what's the cosine of 3 pi? Negative 1. So this will be a -2 plus 1 equal -1. That's out of there too. So, looks like we have our maximum here at pi halves 3 and the minimum here at 7 pi 6 comma negative 3/2. All right, let's see how the book did. Well, I messed up. We got that one right and that one right, but this one down here, I must have negated and negated and negated and negated. Yeah, let's see what we got. Oh, this is the one I messed up. Okay. All right. That's -1 and cosine of 11/3 pi.
I think it's supposed to be just positive 1/2.
Positive 1/2. Okay. I was thinking that might be the case. That's why I was hesitating before. It's going around and around and around the circle too many times. So it starts here and what is it? 11/3 pi. So this is 6/3 pi, 7/3 pi, 8/3 pi, 9/3 pi, 10/3 pi, 11/3 pi. Yeah, you're down here. That's positive. Cosine is positive in that quadrant. So yeah, that's a positive 1/2. So this will be another -3/2. So you have two minima there. Okay. The second one's at 11 pi over 6 negative 3/2 again. Okay. Two relative minima, two absolute minima, one absolute max. And the endpoints didn't come into play at all on this one. Okay. Careful with those tricks. Okay. Use your calculators. They'll usually get them right. All right. Any questions on those? Okay. Homework exercises here. Do any of the odds 7 through 11. They're all at Calc Chat. 7's at Calc View. Either 13 or 15. They're both at Calc Chat. Any of the odds 17 to 21. They're all at Calc Chat. 17's at Calc View. Do any of the odds 23 to 39. They're all at Calc Chat. 25's at Calc View. Either 41 or 43, they're both at Calc Chat. 41's at Calc View. either 45 or 47. They're both a calc chat. 49's a calc chat. 51's a calc chat. 53's a calc chat. Now those last several, they say you need a graphing utility. I really think you can do some of those, if not all of them, without a graphing utility. But anyway, I said 53's a calc chat. 55's a writing thing, so if you see something there that might make you interested in a paper topic, I can't see it, but if you can get a couple pages out of that, you certainly can. You can explore doing 57 and or 59. Then some applied problems are either 61, 63, 61 or 63. They both should be at calc chat. There's a couple true false, 65 and 67. They should be at calc chat. And then 69 is a function type problem. You can take a look at that if you would like. Any questions? 3.1. Okay, I think we've got time to proceed to 3.2. Where is my, whoops, there it is, 3.2. Now, if you'll notice here, just since I got it up here, Chapter 3 is a little bit longer. We did 5 sections in 1, 5 sections in 2. We may not do all 9, but Chapter 3 does have 9 sections. I can't remember if we'll do all 9 of those. I think probably not. There's probably 1 or 2 we skip, just like we skipped 2-6. But got a little bit more time. But so far, these sections are pretty short. So we may still move through them pretty quickly. Please get your test done. If you haven't done the first test, get that in so you can be working on your second test. Because summer things come fast and furious. Let's get the slideshow set up. All right. Any questions so far? Still in Chapter 3, applications of differentiation. In 3.2, we're going to talk about Rolle's theorem. There's another potential paper topic. Who in the world is Rolle? I don't even, can't even remember what his nationality. I'm guessing French, but I don't know that for sure. Rolle's theorem and the mean value theorem. So we're basically going to talk about 2 theorems, and I'm sure their applications, okay? Especially since this is application of differentiation. So our objectives here are to understand and use Rolle's theorem and to understand and use the mean value theorem. So let's start with Rolle's theorem. All right. The extreme value theorem, which we just did earlier, states that a continuous function on a closed interval a to b must have both a minimum and a maximum on that interval. That's the one I kept going back to. Both of those values, however, can occur at the endpoints. And we were doing that, always checking. Now, Rolle's theorem, named after French mathematician Michel Rolle, okay, and his lifespan, 1652 to 1719. Here in Alabama, we were wilderness at that time, okay? We were not even close to being explored. I think completely occupied by Indians, you know, so I don't think there were very many, if any. There were probably a few settlers that had going there trading and stuff. Way back, way back. This gives the conditions that guarantee the existence of an extreme value in the interior of a closed interval. Okay? Conditions that guarantee the existence of an extreme value in the interior. Meaning we're going to exclude the endpoints. Okay? So we're going to guarantee the existence of an extreme value in the interior of a closed interval. If f is a continuous function on the closed interval a to b, so that we're back to a closed interval, and differentiable on the open interval a to b, doesn't have to be differentiable at a or b. Now, here's the condition. If f of a is equal to f of b. You've got some place that f at this endpoint is exactly the same as f at this endpoint. These two values are exactly the same. Now, this isn't going to happen all that frequently. But if it does, if these two have the same value, then there's at least one number c on the closed interval a to b such that f prime of c is equal to 0. There's got to be at least one. Remember, f is continuous and differentiable. Okay? To be differentiable, that means it's got to be smooth. Right? So if it's smooth, then if f of a is equal to f of b, then there's at least one number c somewhere in between those two where the first derivative is 0. Now, if you think about this, what if that's just the line f of a equal f of b because they're all on the horizontal line? Well, the f prime is 0 everywhere on the horizontal line. So that's clearly okay. So what if it's not a horizontal line? If it's a smooth continuous function, it's either going to be going up or going down. Okay? If it's not a horizontal line, it's either going up or down. And if it's going up, there's going to be one place there, at least one place. Going down, there's going to be at least one place here. There may be many places in between there, but there's got to be at least one where the first derivative is 0, if it's a smooth continuous function. It's continuous by the definition. Because it's differentiable, it's also got to be smooth. Okay. From Rolle's theorem, you can see that a function f is continuous on a to b and differentiable on a to b, and if f of a is equal to f of b, if those two are the same values, there must be at least one x value in between a and b at which the graph of f has a horizontal tangent. Got to be at least one. There could be several of them if they're smooth and continuous, but there's got to be at least one. Okay? If it's just a straight line, there's an infinite number where it's got a horizontal tangent. Okay? All right. Now that could have gone downward just as well as upward, and it could have gone up and down, but it have a bunch of places that's going to be. All right. And by the way, this is saying at least one, let's go back to the actual theorem, at least one number c in AB for which that's equal to 0, and if that's equal to 0, that's going to be generally at a relative max or relative min. There's going to be at least one that's got to be. Okay. When the differentiability requirement is dropped from Rolle's theorem, f will still be a critical number in A, have a critical number in A to B, but it may not yield a horizontal tangent. Okay? Because of these constants. There, that first derivative doesn't exist. It's not a smooth function, so the first derivative doesn't exist at that point. So that still will give you a critical value, and that's still going to be a local max or min. Absolute max or min. Okay. Here is example 1. I think we've got time for it. Find the two x-intercepts of f of x equal x squared minus 3x plus 2, and show that f prime of x is equal to 0 at some point in between those two x-intercepts. How do we find the x-intercepts? What's true about an x-intercept? When y is equal to 0. Where's the y in that problem? F of x. So you set this equal to, let me get my pen back. Okay. Set this equal to 0. Now what could you do once you set it equal to 0? Two options. Factor, that sounds like a good one. Does that factor? Well, if it does, the first one's got to be x and x. Sign has to be minus minus, -2, -1, right? So this will be at x, what are your two intercepts at? X equal 2, x equal 1. So, those two places, the function's equal to 0. Same value. Okay? Show that f prime of x is 0 at some point in between those two intercepts. You know it's got to be by Rolle's theorem. Same value, okay, at the two inputs, somewhere in between it has to have a first derivative. So basically say Rolle's theorem, yeah, it says it's got to. But let's find out where it is. So what might we do? Good Jesus question. Take a derivative. F prime of x is equal to, a little louder, 2x minus 3. Is that what you said? Say yes? Okay, good. And we want to know where that's equal to 0. We'll set it equal to 0, and what does that give us? 3/2. Exactly midway between those 2 points. Yep. First derivative is 0. Rolle's theorem said it would have 1. This tells you exactly where it is at 3/2. And anyone want to hazard a guess whether that's a minimum or maximum? We haven't done that yet. I just wondered if you wanted to make a guess. You think it's going to be a max? My guess is a min. Why? Because this parabola is a it's got to be a min. Right? We haven't done that. It should be there. Okay. Let's see how they did it. Can I erase it? Note that f is differentiable on the entire real line because that's a polynomial function, differentiable everywhere. Setting f of x equals 0 produces that, and factoring that gives you x equal 1 or 2. Those are the two x-intercepts, or solutions for that. So f of 1 is equal to f of 2. Both of them equal to the same value, 0, of course, if they're equal. Okay. And from Rolle's theorem, you know there exists at least one c on the interval 1 to 2 such that f prime of c is equal to 0. Rolle's theorem tells us that. To find that such a c, differentiate f, and that gives you 2x minus 3. Find out where that's equal to 0, set it equal to 0, and you find out x equals 3/2, exactly halfway between those 2 points. And there it is. And indeed it is a absolute minimum. Okay? It's got to be a minimum in that range there, but this is the absolute minimum for all of them. Horizontal and there. All right. Make sense? That's example 1. They're skipping example 2. The question is, do we have time for example 2? How much time we got? Huh? Oh, come on. Okay. So we will begin next time with example 2. So I'm going back one slide, and we'll do example 2. We'll pick up next time. Let's see, did we get enough for homework exercises? Yes, let's see. I think you might be able to do 3 or 5. They both are at Calc Chat. And I'm almost certain you can do 7 and 9. They're both at Calc Chat, 9's at Calc View. you might look at some of the others. That'll do for now.
Yeah, I know.
Okay. So we'll pick up there for next time. Did everyone who came get a copy of the second test? I know some of you came in late. Did everybody get a copy of the second test? Good deal. All right. Be working on those. You got a weekend coming up right now. Technically due next Wednesday, but if you need more time, you can have it, but get them in before we're ready for test 3. All right, good deal.
I gotta let you know that I'm gonna be going out of the country for the weekend.
Oh,
So I'm not gonna be here Monday.
Monday. Okay. Going
I
back
should
home
be here
or?
by Wednesday. No, my cousin's got a wedding. For some reason, he wanted to have it outside the country, so.
One of those destination weddings.
Mhm.
Well, that means it's expensive for everybody else. Right, okay. Yeah, okay. Well, enjoy, have fun. We'll see you then on Wednesday, next week.
Yes, sir. See you
Okay.
next Wednesday.
All right.
I'm going out of town next week.
Oh, come on. You've already been out of town.
I know, this is the last time.
Oh, okay. All right. All week?
Yeah, the whole week. So I'll get the test to you the Monday.
Okay, that'll be fine. Yeah. Good deal. Enjoy.